Welcome to Network Basics Module 2, Topologies and Cabling. In this module, we're going to cover basic network terminology such as peer-to-peer and client-server. We're going to define what a network is. We're going to define what a LAN and a WAN is. We're going to look into understanding basic network structure, which includes topologies, and how the cables and connections that we use actually play a part in our network. So let's start out by defining what a network really is. A network can be as basic as two computers connected together with a crossover cable for the purpose of exchanging data or sharing resources. A network term that you may have heard before, peer-to-peer, is where you have a network that has two or more computers, and both computers act as a client and a server to each other. There's no involvement of a central server for login identification or the server distributing the data. The hosts in this type of network are both consumers and suppliers of resources. The client-server network is a network architecture based on distributed processing, in which a client performs a function by requesting services from a server. Typically, you would find this scenario in a business environment, where there are 10 or more computers. This also eases management of all the hosts on the network. We've all heard the term LAN, or local area network. The definition of a LAN is all the equipment that resides on a customer's network up until the point where it reaches third-party equipment. So using my office as an example, all the equipment in my office resides on my LAN up until the point where I plug into the DSL modem. The DSL modem is provided by my internet service provider or my ISP. At that point, I am now off my LAN and onto the wide area network. A wide area network, or a WAN, covers a large geographical area. It uses public communications such as phone, satellite, or cable providers to link remote sites, say city to city or county to county or state to state, together to make a nice, large, wide area network. Earlier, we stated that a network was two or more computers connected together to share information. Basic network structure consists of those devices that want to share information and their resources, and the medium that connects them or holds them together. This includes the cable and the other network devices which they're attached to. When we build a network and we connect all the devices together, they form what is called a topology. A topology is the physical layout of the computers, the cables, and other components that reside on the network. Topology is the virtual shape of the network and not the physical shape. An example would be I could have 10 computers set up in a circle. Just because I have them in a circle does not mean that I'm in a ring topology. Depending on how I have them wired to my network equipment, I could be in a star topology. So we're looking at the virtual shape of the network and not the actual physical way the computers are arranged. The first topology we want to talk about is bus topology. This topology uses one main line, or trunk as it's referred to, as a backbone where all the computers are actually connected to. On a bus topology, both ends have to be terminated. There are advantages to a bus topology. It's cost, you're only using one main cable to connect all the computers, and the ease of installation, I'm running one line. The disadvantages are as follows. A bus topology does not cope well with heavy traffic rates. The more traffic on the main trunk, the slower the network is. It's difficult to administer and troubleshoot. There's a limited cable length and number of stations that can be implemented in a bus scenario. A bus topology needs to be terminated at both ends. So if there's a cable break, you will lose the entire network. If you lose a workstation, there's a possibility of losing the entire network. Maintenance costs are usually higher in the long run, and there is performance degradation as additional computers are added to this topology. Bus topology is very common when dealing with coax networks. Since most wired networks are switched Ethernet and not passive Ethernet, the chances of you seeing a physical bus topology is very slim. Although almost all wireless networks today can be viewed as examples of a passive bus. The next topology we want to talk about is a star topology. In a star topology, all the computers are connected to a central device, such as a switch. The advantages: easy to install, centralized cable management, and monitoring. Disadvantages: you have a single point of failure. If your main switch, hub, or router goes down, the entire network will not communicate. Also, you're running cable to each individual computer, so your cable costs are slightly higher. In short, this is the most common topology that you will see in any network. Next is the ring topology. A ring topology are where all the computers are connected in a loop by a single cable. You would typically see this with older protocols such as token ring. The advantages are all the computers have equal access to the network and the signal degradation is low. The disadvantages: there is multiple single points of failure. If any one PC goes down, the entire network's down. Also, moving a workstation or making any cabling changes also brings the network down. The next topology is called a mesh network. You can either have a partial or a full mesh. In a mesh topology, some or all of the computers are connected to each other. This provides fault tolerance and low signal degradation. Telephone service providers often have their routing stations set up in a partial mesh network. The disadvantages of mesh networks: the management aspect and the cabling cost if it's a fully connected mesh network. The next topology that we're going to look at is called a hierarchical or a tree topology. This is a combination of a bus and a star topology. The topology follows the hierarchical pattern where each level is connected to the next higher level in a symmetrical pattern. The advantage of this topology is the point-to-point wiring between segments. That means a PC on a single segment not only has access to its segment, but the entire network as a whole. The disadvantages are that it's more difficult to configure than other topologies, and if a backbone line breaks, the entire segment attached to that backbone or segments attached to that backbone will have no access to the entire network. Last but not least, we have what is called hybrid topologies. A hybrid topology is a combination of any two or more network topologies in such a way that the resulting network does not have one of the standard forms. Here, you see a combination of a bus and a star. Unlike a tree topology, this is a true hybrid of those two standard topologies. The size and topology of the network that you're implementing or working with is greatly influenced by the physical cable that you are installing. Through the evolution of networks, up to today, there's been three types of cables that have been used to install networks: coaxial cable, fiber optic, and twisted pair. There are two types of coaxial cables that are or were used for networks. There's thin coax and thick coax, referred to as thick net and thin net. They're not very commonplace anymore as they've been replaced by twisted pair. Coax cable has a max transmission speed of 100 megabits per second. Twisted pair, or what we call UTP, unshielded twisted pair, is the most popular type of networking cable today. It has 7 different categories. The most common category that you'll see today is Cat5, Cat5e, and Cat6. Inside its plastic sheath, UDP has 4 pairs of wires, 8 total. Each is twisted a different number of twists per inch to eliminate EMI, or electromagnetic interference. Twisted pair has a max run length of 100 meters, and depending on the category you have installed, can transmit up to 1,000 megabits per second, or 1 gig. There's a separate type of twisted pair called shielded twisted pair. It's more common in high-speed network architectures. Shielded twisted pair has a metallic foil-type shield wrapped around its wire bundle inside its sheath. This helps eliminate EMI. The disadvantages of shielded twisted pair is that it's harder to work with due to the thickness. It's slightly more expensive than UTP, and you have to ground the metallic shield at both ends of your run. Shielded twisted pair is primarily used in Europe. If you've ever plugged a network cable into a computer, you've seen a jack that looks like this. This is an RJ45 jack. It's an 8-conductor, compact, modular jack used to terminate unshielded twisted pair cable. RJ45 jacks are engineered to maintain specific Category 5, 5E, 6, or 6 alpha performance, and therefore they must match the category cable they are terminating. There are 2 basic types of twisted pair cables that you may come in contact with: a straight-through cable or a crossover cable. Shown here is a straight-through cable. A network cable is used to connect a PC to a network device such as a hub, switch, or a home router. Shown here is a Category 5 cable wired in 568 alpha standards. This cable will only use pinouts 1, 2, 3, and 6. The second type of cable that we mentioned is a crossover cable. A crossover cable is used for light devices to communicate. A perfect example would be two PCs without a network device connected to each other, two hubs connected to each other, or connecting two switches together. As shown here, creating a crossover cable, you're crossing the receive and transmit cables at each end. That's wires 1 and 3 and 2 and 6. The last type of physical cable that we want to discuss is fiber optics. Fiber optic technology uses pulses of light to transfer information down glass or fiber lines instead of using electrical impulses to transfer information down copper lines. This results in much faster speeds, currently 10 gigabits, but 40 and 100 gigabit standards are currently being ratified. The second big advantage of fiber optic technology is further distances. The variables that affect your distance with fiber optics are the mode that you're using, single or multi, the wavelength of the light that you're using, and the micron or thickness of the core of the fiber that you're using. In the example shown here, single mode fiber at 1550 nanometer wavelength can reach up to 70 kilometers. There are two basic types of fiber optic cable, single mode and multi-mode. Single mode fiber optic cable has a small core and only one pathway of light. With only a single wavelength of light passing through its core, single mode realigns the light towards the center of the core instead of simply bouncing it off the edge of the core like multi-mode does. Single mode is typically used in long-haul network connections spread over an extended area, longer than a few miles. Multi-mode fiber optic cable has a larger diameter core that is much larger than the wavelength of light transmitted, and therefore has multiple pathways for several wavelengths of light to be used within its fiber core. Multi-mode can be used for most general fiber applications, such as fiber to desktop or adding segments to your existing network. Multi-mode comes in two general sizes, 50 micron and 62.5 micron. There's a wide variety of fiber optic connectors available today. The main difference among all the connectors are the dimensions and the methods of the mechanical coupling. Typically, organizations will standardize on one type of connector based on the type of fiber, either multi-mode or single mode, and the type of equipment they're hooking to. Since there's such a wide variety of connectors out there, most network equipment won't come with an actual fiber connection. Most devices come with what is called a small form factor fiber injector port. This allows you to take what is called an SFP transceiver, plug the fiber cable into the transceiver, and then plug the transceiver into a generic injector port, enabling that device to speak on the fiber network. Sometimes you may hear these referred to as a GBIC, G-B-I-C, but there's a difference between an SFP and a GBIC. GBICs are larger in size and usually are found on network devices such as routers. They can take anywhere up to 4 fiber optic feeds. SFPs are smaller, typically have one input, and have less cable variations that you can attach to them. The last device we want to talk about is the Network Interface Card, or NIC. The NIC is the physical and logical link between the PC and the network. Networks transmit data in serial format, and the data bus of the PC moves data in parallel format. The Network Interface Card acts as a translator, converting serial to parallel and parallel to serial. This device physically puts the bits onto the cable. It truly is the device that allows us to interface with the network. This concludes this module, Topologies and Cabling.